Betteridge's law of headlines says that if a title ends in a question mark, the answer is usually no. So, if you saw a video called "Can You Survive Inside a Star?", you'd expect the answer to be a quick and emphatic no. And for most channels, it would be. But this is SFIA, where we believe that if brute force isn't working, you're just not using enough of it. So, spoilers ahead, but the answer to today's titular question is yes. It's not easy, but it may be possible, even without invoking new physics. Because a star isn't a solid ball of fire that you fall into and instantly vanish. It's something far stranger, a layered shooting ocean of plasma, with environments that vary wildly depending on where you are. And in some of those regions, the question isn't quite as absurd as it sounds. So today, we're going to ask what it would actually take to survive inside a star, where that might be possible, and why anyone would even try. What inside a star actually means. When we picture a star, we tend to imagine a uniform sphere of blazing heat, a ball of lava, like a cosmic furnace, equally deadly at every level. But stars aren't uniform at all. They are layered systems, with very different conditions as you move inward. The outer atmosphere, the corona, is incredibly hot, millions of degrees in some cases, but also extremely thin. Below that is the photosphere, the surface we see, which is also thinner than air, and then deeper layers where pressure, density, and temperature all climb dramatically. So inside a star is not one place, it's a whole range of environments. At the deepest levels, near the core, you're dealing with pressures and temperatures so extreme that atoms themselves are being forced together in nuclear reactions. There's no meaningful sense in which anything like structure or a person could survive there. But further out, especially in the upper layers, things get more complicated. The material is still incredibly hot, still dangerous beyond anything we normally deal with, but it's also diffuse, dynamic, and constantly moving, less like solid matter and more like a violent, glowing storm. Going into a star isn't like diving into lava, it's more like falling into an alien weather system made of fire, and that distinction turns out to matter a lot. Density. How thick a star really is. To understand what inside a star feels like, we need to talk about density, how much matter is packed into a given volume, and it helps to anchor everything into something familiar. Water is our baseline, call that 1. Indeed, we often express this as specific gravity, where water is defined as 1 rather than saying 1 gram per cubic centimeter. Air at sea level is about 1,000th of that, while typical soil is about 1.5 to 2, and solid rock is roughly 2.5 to 3 times the density of water. Iron is around 7, and the densest metals can reach as high as 20. Even just going from air to rock spans a range of a few thousand. Stars go far beyond that, but also far below it. Let's start at the dense end. In the cores of stars, matter is compressed to extreme levels. You might guess that supergiants are the densest, and that's true enough, but only at the very end of their lives, when they switch over to fusing heavier elements, and soon thereafter explode as supernovae. Before that, they actually have the least dense cores, though still quite dense on par with metals or the cores of planets like Earth. Our Sun's core is much higher, at roughly 150 times the density of water, when smaller stars like red dwarfs and brown dwarfs, densities can climb even higher, hundreds of times the density of water, approaching conditions where matter begins to behave in partially degenerate ways. And needless to say, white dwarfs are far denser still, and neutrons denser yet, both made of various types of degenerate matter. Less massive stars are generally denser throughout all their layers than their bigger cousins. Brown dwarfs and most red dwarfs are all roughly Jupiter's size, even though they can be hundreds of times more massive, while our Sun is only about twice as massive as the biggest red dwarfs and considerably larger physically, and supergiants are thinner and larger still. This higher density in smaller stars comes from all that crushing mass, without fusion providing a strong outward energy source to heat things up and push them apart. Stars achieve what we call hydrostatic equilibrium, a balance where the outward push of the fusion in the core and the inward pull of gravity even out, setting the size and density of each layer. When something tips that balance, like running out of hydrogen in the core and switching to fusing other elements, that equilibrium resets and the star changes sizes and densities. We see this very clearly in red giants. Now, red giants are interesting because they split the density difference. their cores can be extremely dense, often tens of thousands of times denser than water, especially once helium fusion or core contraction begins. So you have something denser than solid metal sitting at the center, while everything around it is expanding outward. Because as you move away from the core, density drops dramatically. Inside the Sun, you fall from that 150 times water core down through layers only a few times the density of water, then below water, and eventually into something thinner than air. By the time you reach the Sun's photosphere, the visible surface, the density is only about 1/10,000th that of water, less than 8% of Earth's air density. You are no longer in anything like a fluid or a solid. You are in a very tenuous plasma. Emphasis on plasma for later because it will control how we interact with that matter, or rather, how we try not to. As you go further out, density keeps dropping. In the corona, the outer atmosphere, density can fall to a billionth or even a trillionth the density of water. That's far thinner than all but the best vacuum chambers we can make on Earth. Now, red giants push this to an extreme. Their outer atmospheres are enormous, often extending out to the orbit of Earth or beyond, but incredibly diffuse. In those outer regions, densities can drop to levels comparable to interplanetary space, or even thinner, effectively a glowing vacuum threaded with plasma and magnetic fields. Even their photospheres, the regions we'd most likely interact with, are often significantly less dense than the Sun's, sometimes only a tiny fraction of Earth's already thin upper atmosphere. So, when we talk about entering a star, especially a red giant, we're often not talking about plunging into something thick. We're talking about passing through something closer to a vast, superheated fog. At the same time, deeper layers quickly become far denser than anything we encounter on Earth. So a star spans an enormous range, from tens to tens of thousands of times denser than water at its core, and far more in degenerate stars, to billions or trillions of times less dense than water at its edges. And that contrast is what makes the idea of surviving, or even moving through a star, at least worth discussing. Because in some regions, you're not hitting a wall of fire. You're flying through something thin enough that, with the right technology, you might just manage to ride through the storm instead of being consumed by it. Heat versus temperature. The next piece of our puzzle, where we might survive in a star without being instantly obliterated, requires us to clear up one of the most common misconceptions in physics: the difference between heat and temperature. Temperature tells you how energetic the particles in something are. Heat is about how much energy actually flows from one thing into another. And those are not the same. Think of a pot of boiling water and an oven on high. That oven is typically at a higher temperature, but you can stick your hand in it just fine so that you don't touch anything, because the hot air in there is at a very high temperature but contains relatively little total heat. Air is far less dense than water after all, and just won't hold as much energy. What that material is matters too, as some materials, like metals, rack inside an oven, transfer heat very quickly compared to something like a pair of gloves. That's why touching a hot or cold piece of metal is far worse than touching something at the same temperature with lower thermal conductivity. That metal slide in the playground you burned yourself on going down in shorts as a kid, or the flagpole in the winter you got stuck to, were the same temperature as everything around them. You can have something with an extremely high temperature that doesn't transfer much heat to you, because there isn't much material there to carry that energy. A spark, for example, can be hotter than a furnace, but it won't melt steel, because it contains very little energy overall. That same idea applies in a much more extreme way to parts of a star. The solar corona, for instance, can reach millions of degrees, far hotter than the visible surface below it, but it's also incredibly thin. Just aren't that many particles there to transfer energy through direct contact. That does not make it safe, not even remotely. Around a star, radiation, charged particles, and electromagnetic effects all try to dump energy into you in other ways, but it does mean that millions of degrees does not automatically translate into instant destruction the way we tend to imagine. Something can be incredibly hot without being especially good at heating you, and that subtle difference is what opens the door, just a crack. It's the idea that survival inside certain parts of a star might not be entirely impossible. Using a star as a braking system, magnetobraking. There's another reason you might deliberately go into a star and has nothing to do with hiding. It's about stopping. Interstellar travel has a simple problem. Getting up to speed is hard, but slowing down is often harder. If you're moving a significant fraction of light speed, you need to shed an enormous amount of kinetic energy when you arrive. One option is to use a star. At first glance, that looks like aerobraking, like dipping a planet's atmosphere to slow down through drag. And you could do that. These are thousands of times less dense than air, which lets you hit them at far higher speeds than we ever would during normal aerobraking, so thousands of kilometers a second is plausible. If you pass through the outer layers of a red giant or a red supergiant, you would experience drag from that diffuse plasma and bleed off speed. You might think braking in hot gas was an issue, and it is, but at velocities we're talking about, say 10% of light speed, the temperature of those particles, a few thousand Kelvin, is almost irrelevant. What matters is your speed. At those velocities, even a very thin gas carries enormous kinetic energy relative to you. Every particle you collide with hits like a tiny bullet, and that energy mostly turns into heat. So you don't actually want to collide with that material if you can avoid it. Instead, you push it away. Using powerful magnetic fields, you can deflect incoming charged particles before they ever hit your hull. Rather than plowing through a star, you're interacting with it, slowing down by transferring momentum into the plasma without absorbing all that energy directly. You're not aerobraking, you're magnetobraking, and conveniently, a star gives you the power source to do that. As you approach, you deploy large reflective sails or mirrors to capture stellar energy. As a solar sail, those can help you brake a lot as is, and red supergiants are the best place to do this, as you can begin serious braking very far out compared to our own sun. Those same systems can double as thermal protection, reflecting incoming radiation rather than absorbing it. The energy you collect can then be fed into magnetic systems that push against the stellar wind and plasma, bleeding out speed while keeping heat loads manageable. You can also use this to turn off into any vector you want, and it's a relatively stealthy way of doing it too. You might still allow some controlled drag, letting parts of a sail or the outer structure gradually blade away to shed energy, but the real work is being done by fields, not hulls. And with a red supergiant, you have room to do this. These stars can be enormous, hundreds to over 1,000 times the radius of our sun. That means their outer atmospheres can stretch across distances comparable to the orbit of Jupiter or beyond. At 10% of light speed, you're covering about 30,000 kilometers per second. So even crossing a distance of 1 billion kilometers, a typical scale for a large red supergiant, takes on an order of several hours to over a day. That's not a quick dip. That's an extended braking maneuver inside a star, long enough to meaningfully shed velocity at survivable g-forces, harvest energy, and potentially arrive in a system without needing to carry all your deceleration fuel with you. You could slow a lot while approaching with solar and magnetic sails, slow more as you pass through the star, maybe slow more, scooping hydrogen as you pass, and then use that as a propellant when you emerge. And anywhere you can do that reliably, it becomes a natural hub. Because in interstellar travel, the places where you can slow down safely are just as important as the places you can reach. So maybe you travel 1,000 light years at 20% of light speed to a red supergiant, and either settle there or slow there to 5 to 6% of light speed to head to a nearby star a shorter distance away to settle. I've talked before about how black holes and red supergiants might tend to become local sectoral capitals. They are energy rich and allow these speed-braking maneuvers. You could probably send an arc ship or fleet out of the solar system at arbitrarily high speeds, but they cannot brake on their own from such speeds, not with onboard fuel. There's going to be a maximum speed they can go based on their target system that's going to permit them to safely brake, and it's higher for these two types. Neither is common, and while about 1% of stars are red giants, red supergiants are more like 1 in a million. The stars that can become red supergiants, destined to go supernova, are few in number to begin with, and their red giant phase is short, 100,000 to 1 million years. These will often be near tight clusters of stars, though you have the issue that a supernova is going to hit them soon, but as we discussed before, that's not a real threat to a spaceborne civilization. Even having one cook off in the middle of your trip towards it is not too big a deal unless it happens just as you're arriving, and a neutron star or black hole will be left, which have their own uses. But you might decide you'd rather go for the largest non-supernova candidate red giant with 6 or 7 solar masses or less, due to their longer lifespans and less explosive finales. These are not quite as good, but they will last longer and let you build a civilization around them. They last millions of years, which is 1,000 times longer than our longest-lived historical empires. I think there is a hesitancy to want to live around a star that is in its final days. We need to remember that these are astronomical timelines, and they are also mobile space habitats people would be living in. They can move when the time comes if they don't want to live around that star anymore, and in the meantime have thousands of times more power it is giving off than our own sun does. Of course, some might not want to move away, but into the star instead. Living inside a star. So passing through a star is one thing, staying there is another. You are not building cities down the core. There's no structure that survives that environment in any meaningful sense. If you're living inside a star, you're doing it in the upper layers, around the photosphere and just above it, where density is low enough that you're not instantly crushed, even if everything is still unimaginably hot. And even there, you're not really sitting in that star, you're maintaining a position inside it. Everything about that environment is trying to dump energy into you. Radiation, charged particles, turbulence, magnetic storms. And your survival depends on continuously managing that flow. You're deflecting plasma with magnetic fields, reflecting as much radiation as possible, and radiating heat away as fast as you absorb it. This is not passive survival, it's active, continuous control. You are not enduring the environment, you are negotiating with the star. And that likely means this is not a place for baseline humans like you and I, though we can contemplate that too. It's easier for highly automated systems, machine civilizations, or heavily augmented environments that can tolerate constant radiation in extreme conditions. Now how? How do we live in a fire that hot? We need to begin by noting that it mostly isn't that hot. Our sun's surface, or photosphere, is about 5500 Kelvin, varying by a couple hundred up or down depending on location. There are no known metals or alloys that can survive that. Tungsten tops out at 3700 Kelvin, and tantalum hafnium carbide around 4300 Kelvin. Our sun is rather hot, though, in the top few percent, and the supermajority of stars are under 4300 Kelvin. Indeed, any N-type red star, whether a red dwarf or red giant, sits between 2400 and 3700 Kelvin, so in principle they can use tungsten, and again we do have alloys that can push even higher now. However, the surface gravity of our sun is 28 times higher than Earth, 28 G. As mentioned, red dwarfs are even denser. The biggest, hottest, and least dense red dwarfs, M0s, are about double the sun's gravity, while M9s, the coolest and densest, can exceed 200 G. So temperature-wise, building a cooler red dwarf might sound reasonable, but besides the crushing gravity, the denser environments mean you need to deflect far more particles. Now I am a lot more optimistic about us inventing some sort of artificial anti-gravity technology than I am about anything that lets you violate thermodynamics, the speed of light, or causality. But right now, our only practical way to counter gravity, which we discussed way back in colonizing the sun, is to build a band around the whole object you live inside, an orbital ring, and live on the inside of it, spinning so that centrifugal force cancels out most of the gravity and gives you an upside down 1G. For red giants, the story changes completely. Our sun is expected to expand to roughly 100 to 200 times its current size in its red giant phase, which would drop its surface gravity by factors of 10,000 to 40,000. Larger red giants would be even lower. That's not crushing gravity anymore. In fact, it's so low that they are actively losing mass, with material escaping from them. So instead, you fall back on our classic trick of a rotating habitat if you don't want to live in microgravity. It's also so low in density that you have very few particles to deflect, and actually relatively low light intensity per unit area. Relatively. Red giants are incredibly bright, but only because they are immense, with tens of thousands of times the surface area of their original form. They are cooler, and radiant energy scales the surface area on the fourth power of temperature, so a star at half the temperature emits about 1/16 the light per square meter. Cooler red giants may only emit a few megawatts per square meter, which is still more than 1,000 times what we want hitting us, but we do have materials that can achieve 99.9% reflectivity across wide bands. Not common ones, though. Polished aluminum and silver both fall short, and most high reflectivity materials only work over narrow wavelengths. Spectralon could do it, and we likely can do better than that, and that takes care of most of the incoming radiation. Your next issue is deflecting all that plasma. You can do that magnetically. This handles heat transfer from convective effects and isn't too bad, honestly. It's the reverse of our normal goal with sunlight plasma, like in a tokamak, where we try to keep even more energetic plasma confined. Deflecting it, especially lower energy plasma, is easier, and is much lower energy plasma than you have inside a tokamak. This is stellar surface, not stellar core. I should probably note that you are going to be bouncing around all over inside the star, as they have massive magnetic fields of their own, and you probably are tweaking your field to surf around to the best current real estate. At this point, you now have a way to avoid bringing in most of the heat. Your next problem is getting rid of the heat you're producing inside and keeping things livable. That comes down to having a vastly larger radiative surface area than your living area, or running large thermal conduits out to cooler regions higher up. So it all comes down to how much light you can reflect away and how much charged plasma you can deflect. You need a margin that not only prevents you from cooking from incoming radiation, but also lets you dump your own heat. This is fundamentally the same idea as air conditioning and refrigeration, just taken to an extreme. Think very large reflective spheres, with a very crinkly surface to maximize surface area, but not cross-section exposed to light. They would be clad in magnetic fields, powered off whatever sunlight slips through. The outer layers run hot, while deeper inside you have highly insulated regions, much smaller, where people can actually live. It is hard, especially without major technological improvements, but it is doable. So the next question is, why would you do it? This month we're talking about ocean worlds, and one of the recurring themes is that the sea is not just empty space between places that matter. On many worlds, it may be the place civilization happens. Dark, deep, pressurized, stable, and full of strange possibilities. That is also why Gods and Monsters from Curious Archive on Nebula is such a fun adventure. It explores the deep ocean as a place where real creatures and old myths start to blur together. Krakens, glowing life, giant predators, and ecosystems strange enough to make ancient sailors seem less superstitious, and more like underfunded field researchers with poor lighting. It's a good reminder that Earth already has something very close to an alien world, and Nebula is a good home for that sort of deeper, stranger science and storytelling. You also find my SFIA catalog there, including monthly exclusives, like this month's exclusive Colonizing Ocean Worlds, Subaquatic Settlements, bonus episodes, and regular episodes early and ad-free. You can use my link or the QR code to get 50% off an annual plan, or 40% off lifetime access, and it directly supports SFIA and the other creators making these shows. Why live inside a star? Stars are not just hydrogen and helium. They have planets worth of metal floating in their upper reaches, and they are all ionized, meaning you can scoop them and sort them magnetically. So you live near a star because it's more than just a dangerous place. It's one of the richest environments in a system. Living in a star is another matter, and while it has obvious scientific value, once that's been tapped out, there do remain two very good reasons to be there. First, your sheer mobility as you coast around inside that heaving red giant couples with all that matter above you to provide a very nice defense against attack. Kind of like trying to attack a submarine with aircraft. It's a pretty difficult place to be firing energy beams or raw slugs into. Guided missiles are on the table, but those are subject to interception and are definitely not having an easy time of going through that environment either. And they have to find you, which is the other good reason. If you want to stay out of sight, you can go somewhere dark and cold, or you can go somewhere so bright and chaotic that no one can see through it. A star is the noisiest object in any system. It's constantly emitting radiation, plasma, and magnetic disturbances. Signals get lost, structures get obscured, heat signatures blend in the background. We spend a lot of time looking for things around stars, spend much less time looking for things inside them. Now, there are easier options. A gas giant hides you in its depths, an ice ball hides you in its darkness, but a star hides you in its chaos. It's the hardest environment to live in, but in return, it offers energy, resources, central position, and concealment all in one place. How well you thrive comes down to how well you can reflect away light, deflect plasma, and manage the heat. Do that, and you're not just surviving, you're sitting in one of the richest environments in the universe. Which makes it less of a refuge and more of a fortress. It may be a hard place to survive, but in a hostile galaxy, it may also be the last and only place you can survive.